Welcome to the deep dive. Today we're taking a really critical look at something vital for aircraft safety and comfort.
Absolutely. We're getting into cabin environmental control systems, or ECS.
Right, specifically Chapter 16 of the AMT Airframe course. This is core stuff for technicians.
It really is. This isn't just about components. It's life support, plain and simple. And managing huge stresses on the airframe, too.
Yeah, you got this intersection of keeping the structure intact against pressure and keeping humans functioning in an environment that's, well, it's instantly lethal otherwise.
Exactly. We're talking 40,000 feet, where the engineering is literally battling the atmosphere.
So our focus today isn't just naming parts. We want you, the AMT student, to really get the why behind it, the physiology, the thermodynamics of cooling.
And the maintenance dangers, things like adiabatic compression, handling refrigerants. These aren't trivial points. They're critical safety procedures.
Okay, so let's start with the absolute basics. The environment we're trying to defeat, the atmosphere itself.
Right. So if you look at the air we breathe down here at sea level, composition-wise, it's pretty stable. About 78% nitrogen, 21% oxygen.
And then that last 1% is, a mix of other things, argon, CO2, water vapor, ozone.
Exactly. Now, here's the key thing people sometimes get wrong about altitude.
Yeah.
As you go higher, that 7-8-21 ratio, the nitrogen to oxygen proportion, it stays remarkably constant, pretty much all the way up to 50 miles.
Okay, so the percentage of oxygen doesn't really change much where planes fly.
Correct. What does change drastically is the total amount of air above you, the weight of that air column.
Which means the pressure plummets.
Precisely.
Right.
And that is the problem. It's not a lack of oxygen molecules floating around. It's the lack of pressure pushing those molecules into your lungs and bloodstream.
Got it. So pressure is the key driver here.
It is. Oh, and speaking of that 1% ozone O3, it's mostly up near the top of the stratosphere, great for filtering UV light.
But not so great if you breathe it in concentration.
Right. At high altitudes, aircraft can ingest ozone. It's corrosive, it's toxic, so ECS systems often have ozone converters or filters to scrub it out or turn it back into breathable O2. That's a maintenance point, too.
Okay, so the main physiological danger we're fighting with ECS is hypoxia.
Yes, hypoxia. That sluggishness, the confusion, the physical impairment that comes from not getting enough oxygen into your system.
And it all comes back to that pressure relationship.
Absolutely. Your blood absorbs oxygen based on its partial pressure in the lungs. Down here at sea level, that partial pressure is about 3 psi. That's enough to get your blood pretty much fully saturated with oxygen.
But as you climb,
the total pressure drops, so the partial pressure of oxygen drops too, and the efficiency of that oxygen transfer just tanks.
let's put some numbers on that because these altitudes are critical for understanding system failures. Below 7,000 feet.
Generally, okay. Saturation is good.
But hit 10,000 feet mean sea level.
Now your blood oxygen saturation drops to maybe 90%. You might not notice it immediately, but over a few hours. Headache, fatigue, definitely starting to feel it.
Okay, but the real danger zone starts higher, around 15,000 feet.
Yeah, 15,000 MSL is serious. Saturation is down to around 81%. Now you see clear, dangerous symptoms. Sleepiness, cyanosis, that's the blue tint to lips and fingernails. Vision gets blurry, judgment is impaired, motor skills degrade.
Basically, you're becoming unsafe to operate the aircraft or even help yourself.
Exactly, and it gets worse fast. Go up to 25,000 feet without supplemental oxygen or pressurization.
What happens in it?
Saturation plummets to maybe 50%. Unconsciousness follows within about 5 minutes. That time of useful consciousness is incredibly short.
Wow, okay, that really underscores why these systems need to be reliable and, for passengers, deploy automatically and quickly.
Absolutely non-negotiable. Now, something that can confuse people because the symptoms overlap is hyperventilation.
Right. Dizziness, confusion, feeling breathless. Sounds like hypoxia.
It does. But the cause is the opposite. Hyperventilation is breathing too fast, usually due to fear, panic, maybe pain. You're blowing off too much carbon dioxide.
And that's bad because it seems counterintuitive. You're breathing fast, getting lots of air.
Yeah, but your body uses CO2 levels as a signal for breathing and blood vessel diameter. If CO2 drops too low, the body kind of thinks, okay, we have plenty of oxygen. And paradoxically, blood vessels, especially in the brain, constrict.
Ah, so less blood flow, even with enough oxygen available, leads to those same dizzy, confused symptoms.
Precisely. The fix isn't more oxygen, it's slowing the breathing rate to let CO2 levels build back up to normal.
Okay, one more hazard before we talk solutions. Carbon monoxide, CO.
The invisible threat. It's a byproduct of burning fuel incompletely, colorless,
And
odorless.
deadly because of how it interacts with blood.
Right. Hemoglobin, the molecule in red blood cells that carries oxygen, loves carbon monoxide. It binds to CO something like 200 to 300 times more readily than it binds to oxygen.
So the CO effectively kicks the oxygen out and hijacks the transport system.
That's a perfect way to put it. Your body can't get the oxygen it needs, even if you're breathing perfectly good air otherwise.
And the onset is tricky, right? Not like a sudden choking.
Very insidious. Drowsiness, headache, confusion. It creeps up on you. And low levels over a long time can be just as bad as a short high-level exposure because the CO builds up in your system.
For the AMT student, where's the main risk for CO leaks?
Primarily in aircraft with specific heating systems, those that use exhaust shrouds where cabin air is heated by passing over the engine, exhaust manifold, or dedicated combustion heaters. A crack in that exhaust system.
Can pump CO straight into the cabin.
Exactly. So maintenance involves really careful inspection, crack testing, leak checks on those heater cans and ducts.
And detection, since you can't smell it.
There are chemical detectors, little patches that change color in the presence of CO. And increasingly, digital sensors that measure CO in parts per million and sound alarms. Finding and fixing the leak source is paramount.
Okay, so we need pressure, but the first line of defense, especially in emergencies or for supplemental use, is increasing the quantity of oxygen. Let's talk about gaseous oxygen systems, GOX.
Right, the standard green bottles. Pure oxygen gas stored under high pressure, and the #1 safety rule.
Don't mix with oil or grease.
Ever. Pure oxygen and petroleum products can react violently, explosively. Absolute cleanliness is mandatory during servicing. Tools, hands, fittings spotless.
So the storage itself, those cylinders, what are they made of?
Traditionally, heavy steel tanks, rated for pressures around 1800 to 1850 psi.
Heavy, though.
Very, which is why newer aircraft use lightweight alternatives, often an aluminum shell wrapped with high-strength fibers like Kevlar.
Lighter, but just as strong.
Yep, and sometimes they have advantages like longer times between required tests. These composite bottles, maybe certified under DOT specs like SP8162, might go 5 years between hydrostatic tests, whereas steel is usually 3.
Okay, explain hydrostatic testing. What's involved?
It's the proof test for the cylinder's integrity.
Yeah.
You fill it completely with water, because water is incompressible, and then pressurize it, usually to 5/3 of its working pressure rating.
So if it's rated for 1800 psi, you test it to 3000 psi.
Exactly. And you measure how much the cylinder expands under that pressure, and crucially, how much it stays expanded after the pressure is released. That's the permanent expansion.
And if it stays expanded even a tiny bit?
It's done. Condemned. Its structural integrity is compromised. No second chances.
Beyond the bottle, the oxygen itself needs to be special grade, right?
Yeah.
Aviators breathing oxygen.
Yes. The main difference isn't purity, it's dryness. It has to be incredibly dry. The specification limits water content to something minuscule, like 0.02 milliliters per liter.
Why so dry?
Because at high altitudes, it's freezing cold. Any moisture in the oxygen lines, regulators, tiny orifices, it will freeze solid. Block the system completely right when you need it most.
Makes sense. And there was that rule about never letting a cylinder pressure drop below 50 psi, even when empty. Why is that?
It's about preventing contamination ingress. If the pressure inside drops too low, especially if the cylinder cools down, it's possible for ambient, moist air to actually get sucked back into the cylinder.
Introducing moisture and potentially causing internal corrosion.
And that icing risk we just talked about. Keeping that positive pressure prevents backflow.
Now, instead of carrying heavy bottles, some aircraft generate their own oxygen. OBOGS.
Onboard oxygen generating systems. Very common in military jets, starting to see them in commercial applications. They eliminate the logistics of refilling bottles.
How do they work? Is it chemical?
No, it's physical separation. They typically use something called a molecular sieve. Bleed air from the engine is passed through beds of a material, usually a synthetic zeolite.
Okay.
This zeolite material has pores sized just right to trap the larger nitrogen molecules under pressure, but let the smaller oxygen molecules pass through.
So it filters out the nitrogen, leaving concentrated oxygen.
Essentially, yes. It's often a pressure swing adsorption process, pressurized to trap nitrogen, then vent to release it, cycling between beds to get a continuous flow of oxygen-rich gas for the crew. Pretty clever.
Okay, so we have the oxygen source. How do we deliver to the person? Let's start with the simplest. Continuous flow.
Continuous flow is just that open the valve, oxygen flows constantly at a rate set by a calibrated orifice in the mask or line.
Simple but wasteful.
Very wasteful, since you're only inhaling about a third of the time. Oxygen flows during exhale, pauses. Passenger masks in pressurized planes typically use this. They drop from the PSU overhead.
PSU, passenger service unit?
Right, they drop into depressurization, but the passenger must pull the mask down towards their face.
Why is that pull important?
That action pulls a lanyard connected to either a little firing pin that punctures a seal or opens a valve directly. It physically starts the oxygen flow to that mask. If you just look at it hanging there, you get nothing.
Good to know. How do we make continuous flow a bit more efficient?
Rebreather masks or reservoir cannulas, they have a small bag or tube that captures some of the exhaled air which still contains unused oxygen and mixes it with the incoming fresh oxygen.
So the first part of your next breath is this oxygen-rich mixture from the bag.
Exactly. It cuts down waste significantly while still ensuring you get enough oxygen, especially on that critical first part of the inhalation.
Okay, moving up in efficiency. Demand systems.
Demand systems are smarter. They only deliver oxygen when you inhale. You create a slight negative pressure by breathing in, and that triggers the regulator valve to open.
Conserves a lot more oxygen.
A lot more. Requires a good mask seal, though. The most common type for flight crews is the diluter demand regulator.
Diluter, meaning it mixes oxygen with something.
Right. At lower altitudes, it mixes pure oxygen with cabin air. As you climb, an aneroid bellows inside senses the decreasing ambient pressure and automatically increases the proportion of pure oxygen.
Until
About 34,000 feet, typically. Above that, it delivers 100% pure oxygen on demand.
But what if even 100% oxygen isn't enough? Like really high altitudes, 40,000 feet plus.
Then you need pressure demand. At those extreme altitudes, the ambient pressure is so low that even breathing pure oxygen doesn't create enough pressure gradient to saturate your blood properly.
So this system actually forces the oxygen in.
Under positive pressure, yes. It overcomes the low ambient pressure and ensures oxygen gets into the lungs effectively. It feels a bit weird, like the mask is actively inflating your lungs slightly, but it's essential for high-altitude flight crew.
And technology keeps refining things. Electronic pulse demand?
Right.
EPD.
Yeah, EPD is a modern take, often used to enhance continuous flow systems or as a standalone. It uses electronic pressure sensors to detect the very start of inhalation.
And then
It delivers a very precise, short pulse of oxygen right at the beginning of the breath when it's most effective for gas exchange. Then it shuts off for the rest of the inhalation and exhalation.
super efficient then.
Very efficient. Can save a lot of oxygen compared to older methods.
Okay, briefly, the other ways oxygen is stored. Liquid oxygen, LOX.
LOX. Oxygen cooled down to a liquid, pale blue, boils at a frigid -183 degrees Celsius. Its big advantage is storage density. A tiny volume of liquid makes a huge volume of gas.
But tricky to handle.
Extremely. Needs special vacuum-insulated containers called Dewar flasks. Handling requires specialized training and equipment because of the intense cold and high expansion rate. Mostly used in military and some medical applications, not common in civil aviation due to cost and complexity.
And the emergency backup. Chemical oxygen generators.
Right, often called oxygen candles.
Yeah.
Usually sodium chlorate mixed with a binder and an igniter. When the mask is pulled, it triggers a firing pin or an electric match that starts the chemical reaction.
And it produces oxygen as it burns.
Yes. But the critical thing for anyone handling these maintenance crew, cabin crew, is that once you start that reaction, you cannot stop it. It will burn until the chemical is consumed.
And they get hot.
Very hot. They produce oxygen for maybe 10 to 20 minutes, enough for an emergency descent. But they have to be treated as hazardous materials for storage, shipping, and disposal.
Okay, so we've covered adding oxygen. But the real engineering solution for high-altitude flight is pressurization, tackling the pressure problem itself. Sea level pressure is 14.7 psi.
And as we said, it drops off fast. Plus, temperature drops too. In the troposphere, where most planes fly, it gets colder by about 2 degrees Celsius, or 3.5 Fahrenheit, for every 1,000 feet you climb.
So the pressurization system needs to provide warm air too, not just pressure.
Definitely. You need pressure for breathing, warmth for survival. Let's define some key pressurization terms. First, cabin altitude.
That's the pressure inside the cabin expressed as an equivalent altitude, right?
Exactly. You might be flying at 39,000 feet, but the pressurization system aims to keep the cabin altitude feeling like, say, 8,000 feet or even lower on newer planes. Much more comfortable and physiologically safe.
Then there's cabin differential pressure, PSID.
This is the big one for structural stress. It's simply the difference between the pressure inside the cabin and the ambient pressure outside.
And that difference can be huge at cruise altitude.
Oh, yeah. Smaller planes might run 3.5 psi differential. Big jets can be 9 psi or even more. That's a massive outward force pushing on every square inch of the fuselage.
And this is where metal fatigue becomes a huge concern, especially on older aircraft.
Absolutely. Every flight involves pressurizing on climb out, holding that differential pressure for hours, then depressurizing on descent. That cyclic loading stresses the aluminum skin, the window frames, the door surrounds.
Leading to cracks over time if not managed and inspected properly. The reason for those aging aircraft programs.
Precisely. Early jet accidents, like the de Havilland Comet disasters, were traced back to catastrophic structural failure due to metal fatigue caused by these pressure cycles. Lessons learned the hard way.
Okay, third term. Cabin rate of climb or descent.
This is about passenger comfort, mostly avoiding ear pain. Even if the aircraft is climbing or descending very rapidly, the pressurization system changes the cabin pressure much more slowly and smoothly.
Typically around 300 to 500 feet per minute change in cabin altitude.
Yeah, something in that range. Keeps
Yeah.
the pressure changes gentle on the ears.
So where does this pressurized air come from? Depends on the engine type, right? Let's start with reciprocating engines.
Recips, your typical piston engine planes usually don't fly as high. They often use engine-driven compressors. A turbocharger is very common, uses exhaust gas energy to spin a turbine that compresses intake air. Some of that compressed air is bled off for the cabin.
Or a supercharger, driven mechanically by the engine.
Yes, or sometimes a dedicated compressor like a Ruth blower or a centrifugal type. But these systems generally limit the aircraft ceiling to around 25,000 feet, maybe a bit higher, due to efficiency limits.
And the big risk with these sources is contamination, isn't it?
Huge risk. Turbochargers and superchargers share oil with the engine. If seals leak, you can pump engine oil fumes, maybe even exhaust gas if there's a crack, right into the breathing air. Constant vigilance needed during maintenance.
Okay, what about turbine engines? Jets and turboprops fly much higher.
They have a much better source, bleed air. Air tapped directly from the compressor section of the turbine engine.
Before the combustion section.
Yes, so it's clean, no combustion byproducts. But it's very hot due to compression and at very high pressure.
Does taking bleed air affect engine performance?
It does impose a small penalty, slightly higher fuel burn, slightly less thrust because you're taking energy out of the engine cycle, but it's the most efficient and reliable way to get large volumes of high-pressure air.
And that hot bleed air then goes where?
Straight to the air conditioning pack to be cooled and regulated before it goes into the cabin. We'll get to that system next.
Are there other ways turbines get pressurized air?
Sometimes. You might see a jet pump, which uses a small amount of high-velocity bleed air to suck in and pressurize a larger volume of outside air. Or a dedicated turbocompressor, basically a separate small turbine driven by bleed air that compresses outside air just for the cabin.
Okay, so we have a source of pressurized air flowing into the sealed fuselage. But how do we control the pressure inside?
That's the job of the outflow valve. This is the crucial regulating component.
It controls air going out, not coming in.
Correct. The inflow from the engines or compressors is relatively constant. The outflow valve, usually located near the back of the aircraft, maybe on the aft pressure bulkhead, acts like a controlled leak. By modulating how much air it lets escape, it precisely controls the pressure building up inside.
How does it know what pressure to maintain? What are its control modes?
There are typically two main automatic modes. First is the isobaric mode. Isobaric means constant pressure. In this mode, the controller adjusts the outflow valve to hold a specific, pre-selected cabin altitude, say 8,000 feet, while the aircraft is cruising.
But what happens when the plane climbs so high that maintaining 8,000 feet would exceed the structure's pressure limit?
That's when the system switches to the second mode, constant differential mode. As the differential pressure per sed approaches the aircraft's certified limit, maybe 9 psi, this mode takes over.
And what does it do?
It allows the cabin altitude to climb slightly, just enough to ensure that the maximum safe pressure difference across the fuselage skin is never exceeded. It prioritizes structural integrity over maintaining the absolute lowest cabin altitude.
Makes sense. Safety first. What about backup safety features? What if the outflow valve fails closed?
That would lead to overpressurization. So there's always a cabin air safety valve. It's essentially a big pressure relief valve, often spring-loaded or pneumatically operated, set to automatically pop open if the cabin pressure exceeds a certain maximum safe differential, like maybe 9.5 psi. It vents the excess pressure overboard.
And what about the opposite? Preventing the outside pressure from becoming higher than the inside, maybe during a rapid descent.
That's the negative pressure relief valve. This is a smaller valve, often integrated with the outflow valve or located nearby, designed to open inward. If outside pressure exceeds inside pressure, it lets ambient air come into the cabin to equalize, preventing the fuselage from being crushed inwards.
These systems also need to know when the plane is on the ground, right?
Absolutely critical. The weight on wheel switch, also called the squat switch, signals the pressurization system. When the plane's on the ground, the system ensures the outflow valve is fully open, dumping all pressure. You don't want to pressurize on the ramp.
And during takeoff.
Often, throttle position switches signal the system. As takeoff power is applied, the system might initiate a small, controlled pressurization bump just before liftoff, ensuring a smooth transition once airborne without any pressure surges.
Okay, we've got pressure.
Yeah.
But as you said, the bleed air coming from a turbine engine is incredibly hot. Hundreds of degrees sometimes. We need serious cooling.
This brings us to the air cycle air conditioning system, or ASI, often called the PACS.
Right. This is standard on most turbine aircraft. It uses the air itself as the refrigerant, relying on thermodynamic principles, specifically the energy changes during compression and expansion.
Let's walk the air through a typical ASI pack. It starts with that hot, high-pressure bleed air from the engine compressor. Correct. First stop, primary heat exchanger. Think of it like a radiator. Outside ram air is forced across tubes carrying the hot bleed air, cooling it down somewhat.
But it's still pretty hot and under high pressure.
Oh, yes. So the next step seems weird at first. That partially cooled air goes into the compressor section of the air cycle machine, the ACM.
Wait, we compress it again, making it even hotter. Why?
This is the clever part of the cycle's efficiency. By compressing it further, we raise its pressure significantly. And yes, according to gas laws, PV and RT, compressing it rapidly makes it much hotter, but we want that high pressure for the next stage,
Which is?
the secondary heat exchanger. Now, this super hot, super high pressure air goes through another radiator, also cooled by outside ram air. Because the air is now at its highest pressure and temperature, it rejects heat very efficiently to the cooler ram air.
So we compress it to make it hotter, only to cool it down again more effectively.
Exactly. After the secondary heat exchanger, the air is still warmish, but its pressure is high, and a lot of heat energy has been removed.
And now for the big cooling step.
Now that high-pressure, moderately warm air is directed into the turbine section of the same air cycle machine.
The ACM has both a compressor and a turbine.
Yes, usually on a common shaft. The incoming air spins the turbine. As the air does work spinning the turbine, it expands rapidly and loses energy.
And rapid expansion causes a massive temperature drop.
Massive. The temperature plummets. It can easily drop below freezing, sometimes way below like -20°C. This expansion is where the primary refrigeration effect happens. Pure physics.
Wow. Okay, so now we have freezing cold air, but it must be saturated with moisture that condensed out during cooling.
Correct. So immediately after the expansion turbine, the air goes through a water separator. This uses various methods, often swirling the air to create centrifugal force, plus a coalescer filter, like a fiberglass sock, to force the tiny water droplets to combine and drain out.
Got to get that water out before it freezes downstream or makes the cabin foggy.
Exactly. But wait, if the air leaving the turbine is below freezing, won't ice form in the water separator and clog it up?
Good point. How is that prevented?
There's usually a refrigeration bypass valve, sometimes called an anti-ice valve. It senses the temperature right at the water separator outlet. If it gets too close to freezing, say below 35 degrees air or about 2 degrees C, it automatically bypasses a small amount of hot bleed air around the ACM entirely, mixing it back in just before the separator to keep the temp slightly above freezing.
Clever. So it prevents icing itself up.
Right. Now we have cold, dry, conditioned air. How do we get the temperature just right for the cabin?
We mix it with some hot air.
Precisely. Some of the initial hot bleed air bypasses the whole ACM cooling process. This hot bypass air is mixed with the cold air coming out of the water separator using a temperature control valve or mix valve. By varying the ratio of hot bypass air to cold conditioned air, the system can deliver air at exactly the temperature selected on the flight deck or by cabin zone controllers.
And on larger planes, you can control different zones.
Yes, often the flight deck, forward cabin, mid, aft. Each zone can have its temperature fine-tuned using trim air modulating valves, which add small amounts of hot air to the main conditioned air supply going to that zone. Plus, you have individual passenger air outlets, the gaspers, and dedicated cooling for electronic space.
Okay, that's the complex world of air cycle cooling. What about smaller planes, often piston-powered, that don't have bleed air? They use vapor cycle air conditioning, VCAC.
Right. This is much more like the air conditioner in your car or home. It's a closed-loop system using a refrigerant that changes state, liquid to gas and back, to move heat. Importantly, VCAC provides cooling only, not pressurization.
And the refrigerant used today is mostly.
Almost universally R134A. It replaced the older R12, which was harmful to the ozone layer. R134A has a nice low boiling point, around negative 15 degrees F or negative 26 degrees C, which allows it to absorb heat effectively even when making the cabin quite cool.
Safety note for technicians working with R134A.
It's not toxic, but it's extremely cold as a liquid. Contact with skin causes instant frostbite, a cold burn. Always wear safety goggles and gloves, and never, ever mix R134A with R12 or any other refrigerant type in a system. They use different oils and have different properties. Mixing them can cause damage or system failure.
Let's trace the refrigerant through the 4 main VCAC components. Starts at the compressor.
Yes, the compressor is the pump. It draws in low-pressure, relatively cool refrigerant vapor from the evaporator. Its job is to compress that vapor, which makes it very hot and raises its pressure significantly. It can be driven by an engine melt, hydraulically, or electrically.
So, outcome. High pressure, high temperature vapor. Where next?
To the condenser. This is usually located somewhere it can get airflow, maybe in the nose or wing root. It's a heat exchanger, like a radiator. The hot, high-pressure vapor flows through its coils,
And outside air flows over the coils.
carrying away the heat. As the refrigerant vapor loses heat, it condenses back into a high-pressure liquid. Still hot, but now liquid.
Okay, high pressure liquid. Now it needs filtering and storage.
Exactly. It flows into the receiver dryer. This acts as a reservoir for the liquid refrigerant. Critically, it also contains desiccant material to absorb any traces of moisture that might have gotten into the system.
Why is moisture so bad in a refrigerant system?
2 reasons. Water plus refrigerant can form corrosive acids that eat away at components from the inside. Also, any water can freeze at the expansion valve, blocking the system.
And the receiver dryer often has a sight glass.
Yes. If you see persistent bubbles in the sight glass while the system is running, it's a classic sign the system is low on refrigerant.
Okay, high pressure, filtered liquid leaves the receiver dryer and goes to the most intricate part.
The thermal expansion valve, or TXV. This is the metering device between the high-pressure side and the low-pressure side of the system.
What does it do exactly?
It takes the high-pressure liquid and sprays it through a very small orifice into the evaporator coil. This sudden drop in pressure causes the liquid refrigerant to start boiling very rapidly at a very low temperature.
And it regulates how much refrigerant goes through.
Yes, and that's key. It has a sensing bulb, usually attached to the outlet pipe of the evaporator. This bulb senses the temperature of the refrigerant vapor leaving the evaporator. The TXV adjusts the flow to maintain a specific amount of superheat,
Superheat.
meaning the refrigerant is not only fully boiled into a vapor, but heated slightly above its boiling point. This ensures no liquid refrigerant gets back to the compressor, which can damage it. Liquid isn't compressible. The TXV modulates flow to keep that superheat just right for efficient cooling without risking the compressor.
So that cold boiling spray goes into the final component.
The evaporator. This is the coil located inside the cabin air duct. The cold, low-pressure refrigerant boils inside the evaporator tubes. To boil, it needs to absorb heat energy.
Which it takes from the warm cabin air being blown across the outside of the evaporator coils.
Exactly. That's the cooling effect. The cabin air gets cold, the refrigerant turns into a low-pressure vapor. Any humidity in the cabin air condenses on the cold evaporator coils and drips into a drain pan, then overboard.
And if you see ice forming on the evaporator,
Usually means a problem. Could be low airflow across the coils, or the TXV might be stuck open, allowing too much refrigerant flow, or the system might be low on charge, causing pressures to drop too low. It needs investigation.
Okay, we've covered how these complex systems work. Now, critically for the AMT student, let's talk maintenance and servicing, starting with the high-risk area. Gaseous oxygen. Safety is paramount.
Absolutely non-negotiable. We mentioned the oil grease hazard. Beyond that, tools, fittings, even your hands and clothes must be scrupulously clean. Use only oxygen-compatible thread sealants, like specific Teflon tapes, and even then, wrap it carefully, starting maybe 2 threads back from the end so no shreds can get into the system.
Because any contaminant in a high-pressure, pure oxygen environment is a potential fuel source.
Precisely. And the single biggest physical hazard during servicing is something called adiabatic compression.
Explain that. Why is opening a valve too fast so incredibly dangerous with high-pressure oxygen?
Adiabatic means no heat transfer. When you open a valve suddenly, letting high-pressure oxygen rush into a lower pressure line or component, the gas at the very front of that rush gets compressed almost instantaneously.
Like slamming on the brakes at a molecular level.
Kind of. All that kinetic energy of the rushing gas gets converted into heat incredibly rapidly. The temperature at that point can spike extremely high, easily exceeding the ignition temperature of contaminants, seals, or even the metal tubing itself.
Leading to fire or explosion.
Instantly. That is why every valve in a high-pressure oxygen system must be opened slowly. Cracked open just a tiny bit first, let pressures equalize gradually, then open fully. No exceptions.
Okay. When filling or charging an aircraft oxygen system from service carts, how do you manage the pressure safely?
You use pressure staging or cascading. The service cart usually has multiple large source cylinders at different pressures. You start by connecting the source cylinder that has a pressure just slightly higher than the aircraft system's current pressure.
Let them equalize slowly.
Right. Then you close that valve and connect the next higher pressure source cylinder. Repeat until the aircraft system is up to the required pressure. This avoids large, sudden pressure differentials.
And filling pressure needs to be adjusted for temperature, right?
Absolutely. Gases expand when hot, contract when cold. The pressure in the cylinder changes significantly with ambient temperature. You must use the manufacturer's temperature correction chart.
Example.
If the chart says you need 1800 psi at standard temperature, say 70 degrees Kelvin, but it's 100 degrees av day on the ramp, the chart might tell you to fill it to an indicated 1950 psi. That way, when the aircraft gets up to the cold cruise altitude, the pressure will drop back down to the required 1800 psi, ensuring a full charge. If you only fill to 1800 on the hot day, it would be underfilled at altitude.
Got it. When does an oxygen system need to be purged?
Purging is needed if the system has been opened for maintenance, like changing a cylinder or regulator, or if it's been completely depleted of pressure for more than a couple of hours. To remove any air, and, more importantly, moisture that might have entered the open lines. You typically flow dry nitrogen, or sometimes breathing oxygen itself, through the entire system at low pressure for a specified time, maybe 10, 15, 30 minutes, to flush everything out and ensure it's dry before sealing it up and servicing.
Okay, shifting gears to vapor cycle AC servicing. Environmental rules are a big factor here.
Huge. Releasing R12 refrigerant into the atmosphere is illegal under EPA regulations. While R13A isn't currently as restricted, best practice and often shop policy is to recover all refrigerant using approved recovery recycling machines. Don't just vent it.
These machines clean the refrigerant too.
Yes, they filter out oil, moisture, and contaminants so it can potentially be reused, saving costs and protecting the environment.
After a VCAC system has been opened for repair, what's the absolutely essential step before recharging?
Evacuation. You must pull a deep vacuum on the system using a vacuum pump.
Why is vacuuming so critical?
Two main reasons. Remove air, which is a non-condensable gas and ruins efficiency, and, most importantly, remove moisture. Pulling a vacuum lowers the pressure inside the system dramatically.
And lowering the pressure lowers the boiling point of water.
Exactly. Any residual liquid water trapped in the system will boil off into vapor even at room temperature under a deep vacuum. The vacuum pump then sucks this water vapor out. If it's cold outside, you might need to pull a deeper vacuum for longer, or even gently warm components to ensure all moisture boils off.
Got to get that moisture out to prevent acid and freezing. How do we find leaks? Assuming we just fixed one, how do we check our work?
Several ways. Electronic sniffers are very common and highly sensitive. They need to be able to detect leaks losing less than ½ an ounce per year. You can also use special fluorescent dyes added to the refrigerant oil, shine a UV light, and the leak glows brightly. Or just a simple soap bubble solution brushed onto fittings bubbles indicate escaping gas. Sometimes just finding oily residue around a fitting points to a leak.
Once you're sure it's leak-free and evacuated, how do you know how much refrigerant to put back in?
This is critical. VCAC systems are charged by weight. The aircraft maintenance manual will specify the exact charge, usually in pounds and ounces. You use a calibrated charging scale. Overcharging or undercharging severely impacts performance and can damage the compressor. You can't just charge by pressure readings alone.
Okay, system charged, final step. Performance check.
Right. Run the system on max cold for several minutes. Check the air temperature coming out of the vents should typically be down in the 40-50 degrees air range, maybe 410 degrees C, and monitor the pressures using manifold gauges.
What are typical pressures?
They vary a lot with ambient temperature, but as a rough guide, the low side suction might be 1050 psi, and the high side discharge may be 125 250 psi. You really need to compare the readings to the manufacturer's performance charts for the current outside air temperature to know if the system is working correctly. High or low pressures can indicate specific problems like a blocked condenser, faulty TXV, or incorrect charge.
Wow. We've gone from basic atmospheric physics to the fine points of vacuuming an AC system. It really highlights how ECS integrates mechanics, thermodynamics, physiology, all to keep people safe and comfortable.
It's a huge responsibility for the AMT. You're maintaining the structural integrity against massive pressure differentials, and you're ensuring the life support, oxygen, temperature, air quality is flawless, precision, cleanliness, following the manual to the letter. It's absolutely critical, especially with the fire hazards around oxygen.
So for you, the AMP student listening, when you're troubleshooting a pressurization controller or carefully opening an oxygen valve, remember the forces and the physiological needs you're managing. This deep dive really shows how aviation engineering turns hostile physics into the routine comfort everyone expects at 35,000 feet.
And a final thought. Consider the sheer endurance required. Think about that outflow valve, constantly modulating, or the fuselage skin flexing with every single flight. The entire safety of the pressure vessel relies on these components working perfectly over tens of thousands of cycles. It's not just about the initial design, it's about the meticulous maintenance that keeps that design safe for the life of the aircraft. That's where you come in.